Yeah, hello. My name is Hannes, and that's David, and we will talk a bit about trustworthy, secure, modular operating system engineering, which we are currently doing, or another approach to how to robustly implement security protocols. So first of all, the general question of this talk is, what is the trusted computing base, and how can we get it as small as possible, while still having some functionality? And the trusted computing base itself is all the pieces of software and hardware of a system which are crucial for its operation. And if one fails, the whole security of the entire system is jeopardized. So, yeah, well, let's look at a concrete example of the trusted computing base. In this example, I will take an instant messaging client. So, as a trusted computing base of the instant messaging client, we first have the client software itself, being it some implementation in some programming language. So the client software is obviously part of the trusted computing base, because if it contains a bug, you might be able to exploit it and to jeopardize its security. Then, as a next layer, we have the dependent libraries. So the client might use OpenSSL or GNU TLS or any other piece of security cryptography library, or XML stream processing, or whatever. So that is obviously also part of the trusted computing base, as we've seen this year with Heartbleed, which affected OpenSSL and which affected a lot of different applications, which all had OpenSSL as their dependent library. So as a next step, we're not quite finished yet. As a next step, we have the graphical user interface framework, which is most often used in such a client, such an XMPP client. And the graphical user interface actually contains stuff which parses arbitrary binary data, like pictures and fonts, and needs to render fonts and so on. And obviously, there have been bugs in picture parser libraries like libpng, like libjpeg. So this is also part of our trusted computing base. So it grows, and it grows even bigger. So then we have the programming language it is implemented in, or it provides an interface for plugins or so. And that programming language environment, that runtime, is also executed and must be part of the trusted computing base. So if there is a problem in some programming language, let's say PHP, which has a long history of problems, or Java, or Ruby, or Python, or whichever you like. But we're not really there yet. So we also have the big C library, which you unfortunately can't see, but you can see it here a bit. So the C library is also part of the trusted computing base, because it is actually there and you execute it. It's loaded. It's loaded into memory. And the C library contains, around 2,000 subroutines. So if there is one exposed and vulnerable, the whole security of the whole system is exposed. And here on the right side, you also see the operating system, being it Linux or FreeBSD or whatever else. The kernel, which provides you with a TCP/IP stack, and which provides you with hardware device drivers. That also needs to be part of, or is part of, the trusted computing base. And then, last but not least, we also have the piece of hardware, the different pieces of hardware, your disk device, your hard drive, and so on, which all contain some firmware, which is part of the trusted computing base. So it stacks up, and the actual question is, for an attacker, is, what is the weakest link? Which piece is the most easy to attack here? And obviously, I forgot some things, like the compiler needs to be trusted, because if the compiler is an untrusted compiler, it can just inject some arbitrary code into your executable. So what can we do? I'm here to propose how to minimize the trusted computing base, or how to get a small trusted computing base. And what are the different approaches we have seen in the past? Well, the first approach, or one of the popular approaches, is compartmentalization, to just build compartments. And that actually solves the problem if there is a successful attack, the impact is low, the impact is small. So instead of running all services on one machine, on one operating system, you just spread the services to various different operating systems. So each service runs in a separate virtual machine or in a change root environment, which was one of the first things developed there. Then we also have Solaris zones, FreeBSD jails, and Linux containers, which is more lightweight virtualization, currently hyped through Docker. And on the other side, we have the where you actually only run the user space of an operating system. So you share the very same kernel, but you execute different C libraries and different service binaries. Then on the other side, we have the hypervisor approach, such as Xen or KVM or so, where you have a small hypervisor, and on top of that hypervisor, you run all the different virtual machines, which are, each of it is a complete Linux or Unix environment. So it is its own kernel, its own device drivers, its own TCP/IP stack, and so on. And hypervisors such as Xen are used around the world in this cloud thingy. For example, at Amazon EC2 and Rackspace and so on. So compartments is a really nice approach to limit the impact of an attack. But it doesn't really reduce your trusted computing base, apart from that you separate the services apart. Also, the crucial question is, can an attacker escape from a change root or a jail or a hypervisor? So it's part of the trust computing base, and you actually add a bit more software. So that's the other approach, actually, which is to just stack on layers and layers and layers, because each problem in computer science can be solved by adding another layer. And the problem is your setup gets really, really complicated, gets complex. And such layers are, for example, stack protection or firewalls or intrusion detection systems. And the problem here is really that all these layers are also software, and they are part of the trusted computing base. So they need to be trusted. And there have been successful, there have been vulnerabilities in firewall implementations and intrusion detection systems, quite a bit. So you actually open up the attack vector if you add more layers. So, as I mentioned, piling layers, David Wheeler already said all problems can be solved in computer science by adding another layer of indirection, apart from the problem of having too many layers of indirection. So, yeah, that's a state where we are right now. So, the whole system is wrong. Let's start clean slate. Get rid of the old arcane legacy here. So, software systems are complex. Yes, today's communication interfaces are complex because we have a variety of computers. But fortunately, the communication is done via protocols, which are more or less standardized or formalized by the IETF and so on. So the API which we actually need to implement for a clean slate approach is the API of the internet, which might be TCP/IP, DHCP, DNS, HTTP, whatever. Some security, maybe TLS, SSL for authentication, then maybe some Git, some SSH, some IMAP to communicate with the other peers, with the entire world, with the rest of the world. And then another problem in computers is persistent data storage. And I'm not talking here about a hard drive, because a hard drive can fail and will fail. But I'm talking here more about a concept where to put data such that it is encrypted, stored somewhere, and I can actually retrieve it. And only I can retrieve it, not everybody else, because it's my data. So what are the tools for this clean slate approach? Well, we are hackers. Our tools are programming languages, and programming languages have various kinds of abstraction features. And then we have libraries, so stuff which is already there, which we can reuse.
So consider that the programming language is the essential vehicle of expressing a program, and we just dissected an operating system into its parts. So if we're radical in operating system architecture, we can be radical in rethinking how to actually build an operating system anew in terms of programming language, which we think is the essential component. During the rest of this Congress, you will hear a series of talks on a string of high-profile exploits in security libraries that happened throughout this year. And the interesting property is that they're all connected by actual failures in the language, more or less. So we turn to programming language as our basic tool to ensure we're building a more robust, a stronger system. And the idea is actually to have programming language give us the ability to focus solely on the problem and not on the accidental complexity of solving it. So we need abstraction to do that, and we want to achieve code that is small and that corresponds to the expression of the solution and doesn't contain other, not really needed information. So what we do is use functional programming. And the idea is to, well, here's an example of this functional programming. It's sending a function that increments the element by 1 to another function, which operates over a list, and then using that function to transform a list into another one. And the idea is that with functional programming, you want to have the program that's a network of very small, isolated, local functions, which can be freely combined in various ways, so that you don't have to suffer from the complexity of considering which one is executed when, or which one was previous or next. This is our basis for declarative programming, which would be the kind of programming where we get to express the logic of the solution and not all the steps it takes for the computer to arrive at the solution. This is, of course, the simplest example of functional programming we can give you, but you can't expect us to squash an entire programming paradigm on a single slide. One of the functional programming approach is underdefined. Many people have different interpretations of what it means. The one we use in our code actually is statically typed and quite orthodox functional programming. So we have the type system. There's been a sweat of languages relatively recently that did away with types because unit tests or something. Turns out the type system is invaluable in enforcing lightweight properties. We don't have a type system such as more advanced languages, such as, for example, Idris, which can prove properties. We have a type system that can enforce them if we can see them, prove them ourselves, or at least see they hold, and then seal them away, hide them through abstraction, and have the type system propagate that, yes, now everything really holds the way we've seen in the beginning. So type system is a very crucial component to our approach. It gives us the soundness. We kind of, on a basic level, know we're not doing something wrong in another part of the application. And another crucial part to this functional programming thing is side effects. Now, there are definitions of side effects, but my favorite example is that the side effect is your square root function, which, when fed the number 2, starts computing the square root of 2, then stops, goes away, presses the fire missiles button, fires the missiles, comes back, and gives you a 1.4 something something. Side effects are a spook action at a distance, whichever means a chunk of code can use to influence or change the behavior of another chunk of code, which is not explicit through parameter passing and result returning. Side effects obviously create complexity and create horrible complexity. And while definitions of what functional programming is vary considerably with respect to whether side effects are included or not, Q, for example, the entire functional JavaScript movement, we subscribe to a very orthodox idea here. We don't use side effects almost ever. And it turned out that was a really beneficial decision. We don't have variables in the code at all. We just call functions with different arguments. And we don't have exceptions, even though the language has both, maybe very locally. And these things lead to componentization and lead to this ideal of many small functions which can be freely composed, exchanged, switched, and changed as the program evolves without considering more things that are going on. In other words, a functional language made it easier to reason about the program, and that was a crucial enabling factor.
So we have seen the tools which are available for programming, which is basically the programming language. And now we propose to have this clean slate approach, where we just don't have an operating system, but instead we have unikernels. And unikernels are specialized applications. So it's not a general purpose system here, but it's really a small, specialized virtual machine image, which even includes all the system libraries and the configuration. So a unikernel just directly can run on Xen itself. So I will explain here a bit about Mirage OS, which is the research project I'm currently working in, which started 5 years ago in Cambridge. It is all BSD MIT licensed, all available on GitHub. It uses OCaml, which is a modular functional program language. And it can compile to a Xen virtual machine image on ARM or on x86 or whatever. And the size of that virtual machine image is roughly 2 megabytes here in that example for an HTTP server, serving also sites over TLS, so HTTPS implementation. So all the crypto, all the HTTP, all the TCP IP, and all the layers up to the scheduler and whatever you think is inside of that image or is done by that image. So how does Mirage work here? Well, as I said, we have a clean slate approach here, and we just remove all the layers we feel are rather legacy and we don't really need in a customized application. So we don't claim to build a general purpose operating system here, but a framework how to build your own services. And obviously my DNS server doesn't need a file system. Why should it need a file system? Why should it need users, local users? Just need some sort of authentication to do updates, and the other stuff which should be done is the request response on DNS port. So Mirage on Xen, instead of having the hardware and the hypervisor and on top of that the legacy operating system like a network stack, a file system, user process, kernel threads, some programming language runtime, some application binary and some configuration files lying around somewhere on some file system. We instead just have the Mirage runtime, which is an OCaml runtime, and then the application code right on top of that. So we don't have a network stack inside of the operating system and so on, but we have it inside of the Mirage runtime. By using that and by directly executing it on a hypervisor, on a Xen hypervisor, we actually can use single address space because we don't need virtual address space. Why should we need a virtual address space if we only have one process? And we only have one process. Well, it's all event-driven, so we can handle multiple connections at the same time, but nevertheless, we don't have a process management thing going on. And we don't even have a C library in here. In Mirage OS, we have no libc. So a huge bunch of code of code which might contain some security issues is just removed. Let's talk a bit about modularity and what I really mean with that. So modules are a programming language concept here, coming from the standard ML, which then developed further towards OCaml. And modules are the composable units assembling complex systems together. So we can just stick together some modules, and libraries can be parameterized by modules. And in the end, we have then an application using all those various modules. And a module is basically an interface. But inside of ML, there is actually the whole module system is a program language in its own, basically. So you can actually program inside of the module system. And, well, what we use here, so in Mirage OS, we use the modularity from OCaml quite a lot. And that gives us that we can run the very same application code using various systems or various configurations. So as a first example, the old Unix socket process. Down here we have the my homepage, which is the application I'm talking about here. So my homepage is actually that stuff I wrote. And then someone else has written an HTTP server called co-HTTP here. And I can just compile my homepage with co-HTTP and then just run as a Unix TCP/IP socket process. So as a Unix binary inside of an already existing 70s Unix system. A different compilation. So I don't need to change any code here. I'm just using different modules. And I can just have a Unix user space network process using a ToonTab interface. So I can just use the backend in orange there, which is the C code I currently use. And then my own TCP/IP stack and my own Ethernet stack, which is part of Mirage, the ETH and the Mir TCP. And I can just execute the very same application code. After recompilation, I can just execute it as a tuned-up, as a process which listens on tuned-up interfaces. And then, as a third alternative, I can just get rid of the Unix system and just use Xen instead of it. So the only thing I really need from the Xen is a virtual network interface. And I can just compile it with the Xen user space or some Xen libraries, and I end up in a binary, which is this virtual machine running directly on Xen. And I didn't have to touch my application code at all. And that is great to have a modular system, because I can just debug on Unix as a socket process. And then when I want to deploy, I can just one-click deploy on some cloud service or on my own machine on the internet. Small intermission, this is a CUBIEBOARD 2, which is an ARM 820 processor, a dual-core A7, and that actually has the Xen virtualization bits. So we can actually run Xen on that board, and we run a Linaro in the DOM0, and then as the guest operating systems, we can just run Mirage OS. And that is a great small board in order to run experiments on. What about security inside of the Xen domain? Well, inside of Xen, there's this CUBEOS project, for example. And that CUBEOS just puts every device driver into a separate virtual machine. So it compartmentalizes the different device drivers. And each PCI ID can be mapped to a separate virtual machine. So this is compartmentalization, and if one driver is wrong, the attacker can only get access to that small compartment. Well, unless the hypervisor is broken as well. The hypervisor is basically a scheduler which separates the virtual machines and takes care of that and schedules the virtual machines. Inside of the virtual machine, inside of Mirage OS, we just have a piece of shared memory for accessing the packets which come in via TCP/IP, via the network card. And we can also do inter-virtual machine communication by using shared memory. That's also done, well, initially done by CUBEOS, by the vgen library. So what can Mirage do? Well, we do have TCP/IP, we do have some basic protocols like DHCP, HTTP, DNS, IMAP. We have a solution for the storage. We have Ermin, which is a persistent branchable store, which is similar to Git, but completely implemented in OCaml and composable and has various backends, like in memory or on file system, and so on. Then we have transport layer security, a TLS stack. And since Mirage virtual machines are so small, I mean, they are 2 megabytes small or so, we can just do the entire deployment via Git and via GitHub, and just store the small blob inside of GitHub. And that is also great, because if it breaks at runtime at some point, we can just do a binary search, like in Git, what broke it. And inside of Git, we have this small binary blob, but that is all which is needed. There's no external configuration and so on. What about performance? Well, actually, Thomas Leonard measured the performance of Mirage OS on that CUBIEBOARD I was showing earlier. And it is similar to Linux on ARM when we serve static HTTP data. And that is Linux and Mirage OS running as a virtual machine on Xen on CUBIEBOARD. The startup time, because a virtual machine is so small, the startup time is really, really fast. It's so fast that we have a DNS server which just waits for requests. And whenever a request comes in, it replies with the IP address and then also checks whether that virtual machine is running. And if it's not running, it just starts it up. And while the client has requested the DNS query and is waiting for the answer in order to establish a TCP connection, our virtual machine is already booted, because it boots in 20 milliseconds. So it is really services on demand. We don't run all the virtual machines at the same time, but only when they are really needed, when we need them. So let's talk a bit more about TLS. What is this transport layer security? And the reason for talking about that is because we developed this year a transport layer security stack for this Mirage in OCaml from scratch. And TLS is the most widely used security protocol since roughly 15 years. It has been standardized. And it is agile. So instead of having hard-coded key exchange and cipher method, it actually negotiates the protocol version, the key exchange, the cipher, and the hash algorithm to use. So it is rather complex or intricate. There are also 4 different versions of TLS. Well, we didn't implement SSL version 2 and 3 because we felt like, well, time is over. And there's TLS 1.0, TLS 1.1, TLS 1.2, and upcoming there's also TLS 1.3, which we haven't yet implemented. The whole issue of secure communication is basically how to authenticate the other peer, and that is done in TLS using trust anchors, so those certificate authorities using X509 public key infrastructures. And yeah, I will just show you the handshake, because our stack, well, we wrote some we added some tracing features. And within here, you can see a sequence diagram of TLS handshake, which was just produced by my web browser accessing that website, which is a web server I've written using our OCaml TLS stack. And you see here on the left, the client, on the right, the server. I'll make it a bit bigger. Yeah, and those dashed lines are unencrypted messages on the wire, and those solid lines are encrypted messages you can see at the bottom here. So I will start. So first, the first message is from the client, and the client actually sends a client hello, and it says, well, the version I support, the highest version I support is TLS 1.2. Then it sends some nonce, because the client needs some nonce in order to establish secure communications. Then we have a set of cipher suites. So the client says, oh, look here. These are actually all the different key exchange and encryption methods I can use or I implement, and I'm happy to talk here. And then the client also sends arbitrary extensions here. Well, renegotiation extensions for security enhancements, then some elliptic curve stuff and so on. So that is the first packet. And then the server actually chooses which protocol version and which cipher suite to pick. And the cipher suite contains the key exchange algorithm, the encryption algorithm, and the hash algorithm. So in this case, the server says, oh yeah, let's talk TLS 1.2. Here's, by the way, my nonce here. That is the cipher suite we talk. And there is currently an ephemeral Diffie-Hellman using RSA certificates and AES 256 with SHA as the HMAC algorithm. Then the server also sends over its server certificate, and that is the ASN1 encoded X509 certificate, which the client needs to check at some point. Then, since we are doing a ephemeral Diffie-Hellman key exchange here, we need to negotiate, or we need to pick the Diffie-Hellman group and so on. So the server also sends here the Diffie-Hellman group, the generator, and its public over the wire. And then the server ends with the server hello done, which is, well, now I'm done here with my key exchange. You continue, and the client, sends over now its Diffie-Hellman shared, once it verified that the certificate is okay and the server key, so the Diffie-Hellman group and so on is okay. And then the master secret is computed. The master secret is the 48 bytes of data, which are used to derive the symmetric and HMAC keys. And then there's the single message change cipher spec, which is first sent from the client to the server and then from the server to the client. And it says, from now on, we just negotiated on some crypto parameters and some key material. Let's use that. So then the connection switches to an encrypted connection and sends over the finished packets. And the first finished is, well, it also contains a hash in order to authenticate that the whole handshake, the whole binary data of the handshake was received as it was sent, and there was no man in the middle who modified the data because it was all plain text. And the same is then sent from the server side to the client side. And then finally, we are on the layer where we can handle out application data. And application data in this case was an HTTP request, which you can see here. And that was sent from the client to the server. And then obviously the server answers with the application data back. But let's switch back to the slides. We just saw the TLS handshake, a complete handshake of the TLS session, which we first produced, and then sent over via JSON to the client. So the server actually remembered all the packets which were transferred and transferred them back to the client. So let's talk about OCaml TLS. That is our office, early 2014 in Mirleft, Morocco, Africa. We started to develop clean-slate transport layer security stack from scratch without any funding. And it was very early in 2014. I flew there on the 5th of January this year. And David joined later. And it was even before there were those security issues this year in various TLS implementations, like go to fail and heartbleed and change cypherspecs vulnerability in OpenSSL. And various others. I mean, GNU TLS also had some problems. And let's talk a bit about OCaml TLS.
So I guess you know a TLS hipster when he says, I was into it before Heartblade. Yeah, now I'll try to wrap up, or actually go into details, how exactly the thing you've just seen is laid out inside, because that's the important part here. It's not just making, well, another TLS. It's like making a TLS in another way. So we basically have several libraries to handle subtasks which are involved in this security protocol. So we have the crypto library, and we have the certificate library, which basically parses and validates certificates. And we have the overall TLS built on top of that. And the crucial part is that we were aiming for simplicity, but throughout, inside and outside. So we wanted to have the code to be simple, and the code to be not to be prone to the spooky action at a distance, to be easy to reason about. But we also wanted the code to be simple to use. And that's actually a published deficiency of known TLS stacks. There was an actual published paper about how the unwieldiness of OpenSSL's API leads to in-the-wild security problems. And that's because its callback, which is callback to check the certificates, is quite difficult to implement correctly. So we're actually aiming to do something really simple, spot on, and as small as possible for everybody involved. And we have a few libraries to do that. And probably the most interesting one lying below the TLS level is the crypto library. And it's also the one most difficult to defend because, well, you should never develop your own crypto, right? We had to, because it has to run on Mirage, and it had to be mostly in OCaml. So we did this the Nualo crypto library. And, well, the essential trick was to try and not drown ourselves in the potential timing side channel attacks, other than the basic correctness, which is not horribly difficult to achieve. It's actually surprisingly simple to achieve. We have to be mindful of all the other problems that a crypto library can be plagued with. I might expand on that later on if anybody's interested in one talk or something, but as far as timing side channels and garbage collectors go, the trick was to separate the computation and have the very cipher cores, the very crypto cores in C still, to avoid amplification of the timing differences through callouts to garbage collector. So that's our basic defense. What are we doing? Implementing crypto in OCaml. The timing crucial parts are not in OCaml, but most of the complex high-level logic is, and that proved to be simplifying, very much simplifying. So yeah, we have we don't really have much crypto yet, but we have what was necessary to support TLS and later an OTR that Hannes did like for kicks. So we have an RNG, which is thought to be strong. Entropy sources are still debated on, but at least they've been mixed well. We have a few public key algorithms. We have the basic block ciphers, 3DES and Reindl AS. And basically 3DES was for testing, so we have Reindl. And we have a bunch of hashes, which are two SHA families and MD5. And the separation is always the same with the blockade things. The block operations are in C always for speed and to avoid going through garbage collector. The public key crypto is in OCaml, and it was very nice to write it in OCaml because each single algorithm, together with all the utilities in it for it, is about 100 lines of code and very stretched wide. So it's a nice environment to code in. Yeah, and we also have this SN library. Now, SN is this encoding, basically, that was developed in the early 80s by telecom industry and shows. And it stands for abstract syntax notation, which means that it's a language to define the structure of data, and then have the on-the-wire encoding of data be automatically derived from the structure. It actually prescribes the encoding once you give it the structure. And you can see a snippet of it. I'm not going into details, but it's a language in its own right. And it'd be completely irrelevant. It's only used for certificate and I think one other message type in the TLS handshake. So it wouldn't be interesting if it wasn't a notorious sort of attack vector in the past, because the format is tricky to parse. And very often, the other libraries don't really parse it safely. So now and again, bad exploits appear precisely in the SN layer. So this is SN. This is the solution to SN. Yeah, we have something, parser, generated commenters or something. But please do focus on two snippets of code. The previous one and the next one. So if you go over the surface syntax, which is slightly different, what connects those? Not a lot of thinking. And the idea is that we have an embedded language, because the OCaml is a very nice language to embed other languages in. So instead of going and doing all the parsing that's usually been done, we just stepped aside, solved the problem of parsing in isolation, and then built a language like this to express what actually needs to be parsed in the crypto context. So this is one of the examples where usage of OCaml actually shines to separate concerns. We also have the library that deals with certificates, which might actually be extended soon to be a standalone utility for various things you want to do with your certificates. And maybe the most interesting thing to note is the simplicity of its API. Essentially, we have two ways to construct something that authenticates your certificates. And we implement the standard chain of trust, where you provide the library with a set of certificate authority roots, trusted certificates, and it can be queried with another certificate or certificate stack and check itself, parse, validate certs and everything, and check the chain, whether your certificate authorities actually did sign the chain ultimately. And we also have another kind of checking built in, which is checking of fixed fingerprints, which can then be accumulated, which is the basis for trust and first use mechanism. So these are the parts. And then there is the topmost TLS, and this is a mouthful, definitely. But what it wants to say is that the entire network library you've just seen in action boils down to two entry point functions, nothing more. So you have one function to process that data that came from the outside, another function to process data which is to be sent to the outside. And that's more or less it. The type signature of the first one itself is still a mouthful, but what it really wants to say is that it takes two things into three things. It takes whatever describes the state of the TLS session in progress and a byte vector, and produces the next state after processing the byte vector, maybe a byte vector which is intended for the application to consume, and maybe a third byte vector which is the immediate response. And that's all. It doesn't do anything else. It doesn't even keep state. Its state is a value. It's just a description of a session in progress, which you can actually store and rewind back. You get out of sync with the other endpoint, but you can do that. And as for sending, it's also incredibly, oh, just one detail. It maps a pair into triple, but not exactly. It maps a pair into either a triple or a value that describes an error. So the error handling is completely localized in that return value and completely explicit. If you want to run it, you have to check if there was an error. And it's very easy to do. That kind of simplicity we're aiming at. And the other function is essentially give it a state and give it a bunch of byte vectors to process, and it will give a new state and something to send over the network. So this entire apparatus of doing crypto protocol is contained in a pure bit of code that doesn't even know about sockets. It doesn't know about state. It doesn't know about network. It knows about almost nothing. It just takes some values and computes some other values. And that's a really good position to be in when writing a security protocol. And of course, you don't want to use that directly, so that's the core. And then we have some thin shims on top of that, which actually give you more or less idiomatic interfaces to work with for various library setups you might use in OCaml. This, for example, this one example where you can accept a connection if you have the private material and a file descriptor, and you get a pair of channels to communicate on, and the address of the other endpoint. And relatively similar is the connect function. You give it the X509 authenticator, which you somehow synthesized, the other endpoint, and it connects. This is not important. What's important is that if you have a completely pure core, not only you can reason about it, you can also glue it into whichever context you want. This is one of the gluings. We have others, and this is not even the main one, because this is not the Mirage API. We can manufacture however many of those we want, because it's incredibly flexible not to have any interaction with the outside world.
So what is the status of OCaml TLS? Well, I just showed you the TLS handshake, and that was running on our own TLS stack on the server side. And we have that TLS demo server live since July or so this year, and we served over 50,000 sessions, and we successfully served them. So we have interoperability with a lot of different TLS stacks. Well, unfortunately, there aren't that many TLS stacks out there. And we managed to develop a working TLS stack and a robust implementation of a TLS stack in a very short time frame. I mean, it was, what, January this year when we started? So
it was
less than
essentially 3 months to working implementation.
Yeah, it's roughly 3 months to do that. And while doing that, we refactored a lot of times our entire code base. And we learned a lot about how to securely write, or how to write robust implementations of security protocols inside of a functional programming language which has pattern matching, basically. And the statistics, well, I just use here CLog for line counting, and I just counted the entire repository. I didn't strip out anything. And OpenSSL has roughly 350,000 lines of code. Well, fortunately, they are the LibreSSL guys who managed until within a few months to strip out at least 50,000 lines of that code. So that is a great approach. PolarSSL, another small C-based TLS implementation, is roughly 100,000 lines of code. Our code base is currently 20,000 lines of code. And we can interoperate, and we have nearly all the features we actually need to have. And also, well, the interoperability here is shown for the server side, but also the client side works with various different stacks. What is the future? Well, we already have some preliminary pull requests for client authentication, AAD ciphers, and server-side server name identification configuration. What we currently don't have code for is session resumption and elliptic curve cryptography. We might plan to do that or not. It's not that hugely important, I think. But we want to move forward. Now we have a healthy, functional code base, which is rather easy to extend. And we actually extended it by developing OCaml OTR in a very short time frame. In order to do that, we needed DSA support in no crypto, and that was done within less than a week. Our OTR implementation currently doesn't implement the socialist millionaires problem for authentication. but there is only a simple matter of programming now. Then we also have this OCaml TLS is now exposed to all OCaml applications who want to use it. Even we are a framework which is called Conduit, which abstracts over the various kinds of connections you can have. So either shared memory or TCP or TLS or whatever. And the Conduit library is just both server and client side, an abstraction over that. And you just say, oh, I want to talk to that host. And if it's on the same host, the same physical host, you can just have a virtual machine, virtual shared memory connection. And in December, so this month, I also implemented Jackline, which is a command line XMPP client, using our OTR library, our TLS library, and so on. So there's not much C code in this Jackline because, yeah, it's only command line. And here you can see a screenshot. I don't have, at the moment, an internet connection, but I'm happy to demonstrate it to you. And what is a trusted code base in our scenario? So I started this talk with the trusted code base, and I want to also conclude what the trusted code base of Jackline, of my instant messaging client is. Well, it's a Xen hypervisor because it runs on Xen, and on top of then we have a library called MiniOS, which provides you with some stubs and printf functionality. Then we use OpenLibM as a math library. We use GNU GMP for the big number arithmetic. Then we have the OCaml runtime, so the OCaml programming language runtime, which includes a garbage collector and so on. Then we have various OCaml library which we currently use, like cstruct, which is a byte vector, and so on, X509, ASM1, TLS, OTR, no crypto, the XMPP library itself, and so on. And then obviously we also have the OCaml and C compiler. But we don't have any libc in here in the trusted code base, or any huge Linux kernel, because we just don't have it. So, to conclude this talk, I think functional operating systems are real now. I use it. I use Jackline as my day-to-day XMPP client. You might ask, why OCaml? Well, because Mirage OS was there, but there are other approaches, other unikernel-based approaches in Haskell called HellVM, and there's Erlang on Xen, so you can execute directly Erlang on the machine. And I believe, fuck legacy and traditions, let's start to build secure and resilient systems. We phased out, in Germany, we managed to phase out the nuclear energy by 2022 or so. And that's also 70s technology. That's similar to Unix. Let's phase out Unix as well. And let's keep it simple, and the complexity is always the enemy. And just remove the layers of abstractions which we don't need any longer. And join our no libc movement. We also need help. Try it out, try Mirage out, write code, audit the code, break the code. Discuss the code pieces you are interested in with us. Here at the Congress, I'm up there at the Coffee Nerds area, and I'm happy to serve you some espresso while we talk about Mirage and functional programming. Let me thank some people involved. There's, first and foremost, there's Anil Madhavpedi, who started this whole project back in 2009. Then I also would like to thank Peter Sewell, who's a nice guy. He will also talk. He is not here yet, but he will talk on day 4 at the same time in the other room about why computers are so fucked and what we can do about it. And then lots of various other people and all the people I forgot. So that is our talk, and we are happy to take questions and answers.
Okay, thank you very much. Okay, as said, we have about 10 minutes left for a question Q&A. So please, as always, we have 6 microphones in the room. Please line up behind the microphones. For people on the stream and in the internet, we also have a signal angel in the room who can ask your questions in the room. So please write the question in IRC, on Twitter, wherever, and they will get asked. And the first question, please, from microphone number 3.
Yeah, thanks for the talk. Very cool. I was wondering if you lose most of the file system stuff and all that, which usually gives you some entropy, where do you get the entropy from in your reduced kernel?
You don't really get the entropy from the file system. You get entropy from anything you can get entropy from. So you get it from inter-event timings. You get it from your CPU. You get it from your... Actually, it is. Yes, it is. Gathering entropy side effect, but so is using it. And I think we didn't mention it, that structurally, random number generation is a side effect that's retained. We do that side effect. Sorry, we're sorry. We lied. Go home.
But to answer that question, so inside of the Xen domain, inside of a virtual machine, inside of Xen, we actually wrote the host. So in DOM0, we still have some Unix legacy code, and that one feeds some of its entropy to the virtual guests. So we wrote a device for that, for doing that, and for communicating some entropy into the virtual machine. Because otherwise, we are rather low on entropy.
Okay, we take 2 questions from the internet, please.
Yeah, okay, so the first question was asked quite some time ago, so I'm not quite sure if you've already talked to that. Someone asked, how do you account for bugs in the underlying layers like Xen? Do you want to obsolete those layers too? What about hardware vulnerabilities?
Well, at some point we have to start, and starting from real scratch with nothing. I don't think my lifetime is enough for that. So we decided to start somewhere. And currently we trust the hardware, but hopefully more open boards and so on will develop so we can actually verify or do some sort of verification of hardware. And also the same story is true for the hypervisor. There are various projects to start to verify the correctness of hypervisors. And we're happy to switch over to write another backend for the new upcoming hypervisor.
Okay, so the second question was that, as far as I understand, you don't verify your code. Is that correct? And how do you test your code?
So that is correct. I did my dissertation in formal verification of object-oriented code, where we thought a lot about shared mutable state, and that was also tedious to verify. And currently we just write it down, and it looks in this declarative approach, it looks really readable, and you can actually read the state machine from it. And for testing, well, we have obviously interoperability tests, some unit tests, and we are also we are working on a test environment for especially those protocols.
Yeah, if I can expand a little bit on that. The next project we're supposed to do is actually a very comprehensive test suite for TLS. So it's true, we don't do verification, but it's a long story. It's not really clear what to verify at all. There is a verified TLS stack, but they verify crypto soundness of TLS, the protocol. It's not clear what to verify at all, and we don't use the system that would allow us to do that. But we are just about to do a very large test suite for TLS.
So if you give me a specification, a formal specification of TLS, I'm happy to verify.
Okay, next question from microphone number 2, please.
Hi, so do you have plans to have DOM0 written in OCaml or as a unikernel? That's the first question. So DOM0 unikernel. Second is, do you have plans for targeting desktop systems? So specifically doing GUI virtualization using, well, whatever you want to use in that case. And last question, what Xen distribution do you use personally to use your, as you said, you use unikernels to run your Java. What distribution you use?
So in order, no, we don't have a DOM0 and OCaml.
But do you plan?
Not right now, because actually that's a very interesting question. Mirage follows up on the tradition of so-called library operating systems, which were built on exokernels, which means that the kernel only provides for separation and isolation, but not for facilities. I think there were 3 of those systems. All 3 failed due to the difficulty of providing comprehensive driver support. The trick with Mirage is that it runs in Xen, And the trick with Xen is that it runs Linux and unprivileged Linux, but with access to your PCI bus and the rest to get drivers. So more or less, right now, no, we don't have a plan to build DOM0 in OCaml because we would have to cover all the hardware it could possibly run on.
Well, assuming we can get rid of almost all the drivers from DOM0, would that be feasible then?
Excuse me?
If we could get rid of most of the drivers in DOM0, so including GPU, would it be feasible, do you think?
It probably would be feasible to implement DOM0 for
So
something
just the
really
management domain in that case. Yes.
for something really small. We don't have concrete plans. In principle, it would be feasible, but it would be tied to a particular piece of hardware, like a particular onboard. That's the trade-off. DOM0, a general purpose one, gives you hardware.
Okay, so the next question was, do you have any plans for GUI applications? So like desktop applications, web browser, etc.
Not right now. So I'm working on this XMPP client, which is all command line based, and at the moment I'm mainly interested in that because I think that the graphical point and click interfaces, that is a huge amount of work to implement. And we are currently mainly focusing on command line and server side.
Okay.
So.
And what Xen distribution do you use for your use, personal use?
Arch Linux.
Well, I use FreeBSD.
Okay, thank you.
Okay, we give the microphone to someone else, and microphone number 1, please.
Coming back to white lies and state, how do you deal with timing side channels in your crypto library? Because if you re-implement ciphers, you're begging for new timing side channels, and libgmp is not designed for constant execution time of large number multiplication. And some CPUs even leak timing side channel information in their multiply instructions. So.
Yeah, so libgmp was not designed for constant time, of course, because essentially saying constant time big num operations is like saying constant time string length without the length filled. But at that level, where obviously operations vary with the size, at that level we do blending, traditional countermeasures, which are not in the constant time primitive arithmetic operations, but they're a higher up algorithmic level, like RSA blending. This same blending is still not clear in details, but where timing leaks are present in big num code, we just blind them by the usual methods. And I honestly didn't hear the first part of the question. We're asking about timing side channels in low-level cipher code.
If I understand your slides correctly, you re-implemented most ciphers in OCaml.
No, that's the trick. We actually use the reference implementation of Rindle in C. We did not re-implement it. We should switch it at some point to avoid the known cache-based index of array timing leak in Rindle, but right now we have the actual code signed by the original authors of Rindle. The trick is that the code has an unrolled rounds loop, no allocation, and just runs forward. So that's what's in C, everything else is OCaml. We didn't re-implement them precisely not to do nasty mistakes.
Okay, thank you.
Okay, a quick question from microphone number 2, please.
I don't really understand why you think that your OS will be more secure than Linux or Windows. Because now it's a toy OS, you have not much code, okay. But sometimes you will be feature complete and then it will be equal size in FreeBSD or Linux. And just using OCaml will not make your code secure by default.
So in OCaml, we have some language features which prevent certain sorts of attacks, like buffer overflows, because we don't have manual memory management inside of OCaml. So there's a whole area of bugs which we actually prevent. And the other approach is that instead of having 350,000 lines of code, we are currently at 20,000 lines of code.
Yeah, because
it might double to be at the same level of features, but then it's still a factor of 10 smaller than OpenSSL.
I don't believe that.
Actually,
Because reviewing code written in OCaml is much more difficult than say code written in plain C.
In C?
Yes.
Well, it is.
Actually, to properly answer that question, we should compare in detail the code for the tasks or regions that were affected by last year's high-profile exploits in other crypto libraries. And the contrast is more than stark. Something like Heartbleed constitutionally cannot happen at all. Not due to GC, due to memory safety, because we can't reinterpret a key as a buffer or a vector. On the other hand, there are some logical bugs, like chain cipher suit, which is one of quite a bit of bugs in OpenSSL this year, which is a problem in the unwillingness of encoding the state machine in C. And if you just look at the difference between code and how obvious these problems are in OCaml versus how implied they are in C, I think you would believe us.
If you think, okay.
Okay, I'm sorry, but we ran out of time, so please again ask you for a warm round of applause for Hannes and David for their talk. Thank you very much.